Hey everyone, so this is going to be exam review for the final. So this time I'm going to try to pretty much break down everything we've done week by week in a full in-depth and comprehensive guide of every week, right? So I'm going to go week by week and try to do a review of everything we've done because it's been a lot, right? So yeah, as always, best of luck in the exam, and yeah, I'll see y'all there. Okay, so week one. Worksheet wasn't the greatest. A lot of word problems I saw. Not a big fan of it, but I did pull some things out of it anyways, though. So we have average rate of change, we have factoring, domain, and piecewise function. So starting off, we have average rate of change. So this looks like it's like f of x2 minus f of x1 over x2 minus x1. Ooh, it's kind of a bad one. x1, or you can also see it's like y2 minus y1 over x2 minus x1, right? So what it's saying is that, like, we have like our initial point is here, and we have like our stopping point, and we're trying to take the average rate of change. It's the whole thing, right? Okay, that's average rate of change. Factoring. Okay, so let's say I had a problem. I'll make something up right now. Let's see, x squared plus, I don't know, 2x plus 1, right? What do we do here? How do we get to this point, right? What do? We do factoring, right? So we know it's factoring because it's x squared, x, and then like a number, right? So it goes down in scale. So what we do here is to take our number, right? So we have 1, and we're trying to find the factors of 1. So we have 1 times 1, and we have -1 times -1, right? And then we have to add up, or these numbers have to add up to our middle guy, which is here, 2, right? So which one gives me here? Gives me 2, adds up to 2, sorry. This is 2, and this adds up to -2, so our guys are here. So we have x over here, another x over here, like that, and then our numbers are 1, so +1, and we have another +1, so x plus 1, x plus 1. They're the same thing, right? So now we just put this equal to 0. Or I guess I don't need to do both of them, but x is equal to -1. So that's factoring. Oh, this is called the tree method, I believe. And domain and piecewise. Okay, that's a diverse set of things. Okay, so domain. Let's say I have a problem. F of x is equal to x minus 1 over, I don't know, x minus 7, right? What's our domain here? How did we find it? What do we do, right? So for domain is almost always linked to the bottom, like our denominator. So here our denominator is what? It's x minus 7, right? X minus 7. Let's put them equal to 0, and let's find out what we get. So x is equal to what? To +7. So what's so important about this domain thing, right? Essentially, all domain is, why it's on the bottom always, is because we can't have a problem like this be divided by 0. Because in math, anything divided by 0 is impossible. It's called undefined, or what is it? Does not exist, D&E, right? So pretty much when we plug 7 into here, we get what? It's x minus 1 over 0, right? So we can't have that, hence why we have a domain. So our domain here would be, so since we know x can't be equal to 7, right? Our domain is going to be from -infinity to +7, not included, union 7 to infinity, like that. Pretty much this is saying that it could be any number in I don't know, reality, I guess, excluding 7, because 7 in here gives me over 0, which we can't have. And now piecewise. Okay, this is going to be a little oh man, okay, let's see. Let's say f of x is equal to, I have a set of, I don't know, x minus 1, x minus 7. I'm going to reuse these. And then we have x. Actually, no, let's do a number. Let's say I have 4 here. And the conditions are that here, it's going to be, let's see, x is, no, let's say, Yeah, that sounds good. Is equal to 0 if x is greater than 0. Cool. So what is this saying? Piecewise functions is basically 3 different functions, but they're given conditions in order to activate, I guess you want to think about that, right? So we have x minus 1 if x is what? Less than negative 1. So thinking about this, right? No, I should probably do this. Let's draw a number line. That's probably better. Let's draw a low number line. So we have what? Negative 1, 0, and let's think about that. So this is saying that if x is less than negative 1, so we're going this way, right? And what's our sign? It's going to be less than. If it's less than or equal to, then it'd be like a dot. So here we have this. Yeah. I think that makes sense. Yeah. So if x is less than negative 1, our equation or our function is x minus 1, right? So let's say I was given a number, I don't know, like negative 3, right? Let's say I was looking for f of negative 3. Negative 3 has to fit in this condition because it doesn't fit anywhere else, right? So I'm going to plug negative 3 into here. So we have negative 3 minus 1, which gives me negative 4, right? Simple enough. And then my next one is what? X minus 7 if x is equal to 0. At 0, it's going to be x minus 7. So f of 0 gives me what? If I plug 0 into here, I get 0 minus 7, which gives me negative 7, right? And then here, my function is 4 if x is greater than 0. So let's say I was given f of 3, a positive 3, right? I plug 3 into here, and I just get 4. So any number that's bigger than 0, I just get 4. So f of 3 is equal to 4. That's all I've written down for week 1, so that about wraps it up. Next up on the list, we have week 2. We have difference quotient, we have the square root graph, multiplicity, and zero chart, and that's really about it. Okay, so starting off with difference quotient. So difference, wow, that had to be the most elegant writing I've ever done, I'm not gonna lie. Okay, so this is gonna be f of x is equal to f of x plus h minus f of x all over h. So our good old friend, difference quotient, right? So a lot of work. Yeah, I'll do an example problem like later down the line, like when we do the actual review. So, but just know this formula, right? So f of x plus h minus f of x over h. We'll do each individual portion as we go. Okay, now I have the square root graph. So f of x is equal to square root of x, right? So this graph generally looks like this. It's just x-sided, right? It's like this. Our basic key points are going to be, we have, what is it? 0, 1, I think it's 2, right? No, psych. Never mind. So it is 0, 0. Oh, I guess we do 1, and then it would be 4. So square root of 0 is just going to be 0. Square root of 1 is 1. Square root of 4 is 2. So we have 0, 0, 1, 1, and then we have 4, 2, like somewhere down here. Cool. We have that. Oh, multiplicity and zero chart. Okay, so let's do. What can I do here? What can I do? Let's do like negative x squared. No, let's do like negative x to the 5 plus like x squared minus 3, something like that, right? So we have, oh, actually that's kind of ugly. Okay, never mind. Let's do a simple one. Because we got to break this down at some point. So let's say we have negative x squared plus 2x plus 1. Is that even possible? No, it wouldn't be. Okay, let's get rid of the negative. Let's make things a little simpler for ourselves. Okay, cool. So we're looking for our zeros. So this would be 0, multiplicity, and then we have our touch or cross. Multiplicity. Okay, cool. So this is our function, right? So x squared plus 2x plus 1. So can we factor this guy out, right? So let's write it again. Plus 1. Can we factor them out, right? So let's do our tree again. So we have 1. Factors are 1, 1, and -1, -1. So who adds up to 2, right? It's going to be this guy again. So let's go and do our factoring setup. So we have x here. Then we have +1, and then another +1 here. So these two are the same. So okay, so upon review, yeah, this one doesn't really make any sense. So let's change that. So what I did here was wrong. So the right setup here would have been, so instead of doing like that, this should have just been x plus 1 squared, like that. So now when I put x plus 1 is equal to 0, x is still -1, but my multiplicity here is 2. So here, this should have been, multiplicity is 2. So 2 is an even number, right? So even implies that it's touching here at the graph. Touch. So if I were to graph this out, at +2, no, sorry, at -1, so let's say it's like here, it's going to touch the graph. So let's take our key points, right? So let's see. Let's do -2. So -2 into here, we get what? 4 plus, no, this would be 4 minus 4. So 0 plus 1. So a -2 is going to be 1. And then let's take 1 at 0. 0, 0 plus 1 again. So here. And then finally at what point? At -1, it would be at 0. So -2, comma 1, and 0, comma 1. It's going to look something like that. Like a little parabola, right? Because x squared. So that's pretty much it here. I should have done a better question so we have like more multiplicities and more zeros to work with. But this is like pretty much like really basic down, like watered down version. That's really about it for week 2, I think. Yeah. All right. So week 3, synthetic division, long division. Then we have our asymptotes and our wholes. Okay. So I'm only going to go over synthetic division because it's really the most practical one we have. Long division is kind of like iffy. So let's do it outright. So let's say I had a function. Let's say I had f of x is equal to, let's reuse our good old friend, right? 2x plus 1. And let's say I want to check if let's say if I want to check if -2 is like a 0, right? Is a 0 question mark. So is -2 a 0? So first off, right, how do we do synthetic division? So if I'm checking if -2 is a 0, I'm going to put him in like a little corner here. And I'm going to take our coefficients of each one here and put it into like a line. So a coefficient of x squared is what? It's going to be an invisible 1. So invisible 1. We have our plus. Our next in line is 2 because, so we have to take account like of who's here. So the powers really matter. So x squared, here's like x to the 1, and then here's like x to the 0 technically, right? So everyone's here. So let's do 2, and then this guy just bring it down. So, okay, this is a pretty bad example. Let's say it was like x to the 3 plus 2x squared. No, just 2x, right? So in terms of power, right, I have a 3 here and a 1 here. I'm missing the x squared. So if I write this out like this, right, it would be like this guy goes here, and then there's a 0 here in accounting for the x squared. Then this is like our x to the 1. That's how we have to include the 0 here to like make space for whatever we're missing. But here we're all good. So let's do this. And now, so for the first term, we always bring him down. So I've drawn an arrow here. So 1 times -2 gives me -2. So 2 minus 2 gives me 0. So we're all good here. 0 times -2 is 0. So here I bring down this plus 1. So this is our remainder like spot, right? So our remainder is 1 here. So the question is asking if -2 is 0. The answer would be no because we have a remainder. So I forgot to write this down. Sorry. Okay, so we're gonna go ahead and bring this guy down, or no, not bring it down. Like we take 1 off of like the highest power. So here, this would be x like this, 0 here, and then we have a remainder of just 1. Wait, whoa, does that make sense? So let's see, I have x plus 2 out here times x like that, and remainder of 1, if that makes sense. So pretty much this is our, what is it called? Our divisor. So this is divisor, this is our quotient, and this is our remainder. So it's like this. So this times this, and then plus this equals to this whole thing. I forget what this is called, but yeah, this is definitely divisor, this is quotient, and this is remainder. It should look a little longer, honestly, but this is like, you know, some made up question I just made up on the fly. So this is synthetic division though, this is the main setup. Long division I won't do because we won't use it. This is most likely what you're gonna see. Horizontal, vertical, and holes, or horizontal and vertical asymptotes. So, oh boy, let's see. So the best way I can explain horizontal asymptotes is that there's a rule, right? So let's say I had a problem. It's gonna be f of x is equal to, let's say I had x squared over 2x squared, right? So when the highest powers match on both top and bottom, right? So let's say I had imaginary, like, I don't know, not imaginary, sorry, just like this, right? Highest power is gonna be what? X to the 2 on both top and bottom. So when the highest powers match on both top and bottom, the way to solve this out is to take our coefficients on top and bottom for whatever term this is. So here and here, right? So I have an imaginary 1 here. So I'm going to take this coefficient here and divide it by the one on the bottom. So it's going to be 1 over 2. So my horizontal asymptote is going to be, what is it? Y is equal to 1/2, right? Because of this. Let's say I had another one. Let's say I had x to the 3 over x squared, right? So since the top guy is bigger than the bottom one, this is going to be no horizontal asymptote, like that. And then I guess the reverse, right? So if x squared is on top now over x cubed, now here, since bottom is going to be bigger than top, this is going to be y is equal to 0. Yeah, so these are horizontal asymptotes. So let me write that out. Horizontal asymptotes. Okay, so now vertical asymptotes. So vertical asymptotes are always going to be associated with our domain. So let's say I had a problem. Let's say this is going to be, I don't know, x plus 2 over x squared plus, let's see, 3x plus, this or 2. So again, right, from the thing we talked about week 1, how do we get our domain? What do we do, right? So we take the bottom guy and we go ahead and put him equal to 0. X squared plus 3x plus 2 equal to 0. So again, so let's take our number out. So we have 2. What are the factors of 2? We have 2 times positive 1 and then the negative counterparts. Oops. Negative 1. So who adds up to 3? So this guy adds up to 3 and he adds up to negative 3. So it's going to be these two. So set up again like this. So we have plus 2 here and we have plus 1 from here. So end up with this. So now put these equal to 0. Equal to 0. This guy becomes x is equal to negative 2. X is equal to negative 1. So in terms of domain, right, our two numbers that cannot be in this particular equation, they can't be equal to negative 2 and equal to negative 1. Is that right? Yes, it is. So x can't be equal to negative 2 and negative 1. So in interval notation, this would be domain. So this is going to be negative infinity to the most negative guy, so negative 2, not included. Like, oh, I need more space actually. Oops. -2 to -1. And then there's going to be u down here, -1 to infinity. So -infinity to the most negative number out of our set, right? So -2, close parentheses, u. We start up again here, -2 to our most negative guy after this one. So -1, right? U, we pick it back up after like this again to infinity, right? Simple enough. So knowing our domain like this, our vertical asymptotes are pretty much the numbers in this domain. So vertical asymptotes is going to be x is equal to -2 and x is equal to -1. So on a graph, no, that's a different problem. So our vertical asymptotes here would be -2 and then -1. So this would be like a three-piece like graph. So like, I don't know, I'm just gonna draw things out like randomly. Let's say like this was like here. This guy went like here. And then, I don't know, like something like that. This is not like scale, just an example. I just want to show the asymptotes. I don't actually know what this looks like on a graph. But yeah, something like that. So this pretty much covers week 3. So we have synthetic division, horizontal asymptote rules, and then vertical asymptotes. Okay, so week 5, we have inverse functions, we have exponential logarithmic functions, and then domain of log and exponential. So inverse functions, I don't want to do like a whole in-depth thing about it because I don't think we really covered that much about it, right? So let's say I was given that, I don't know, f of 4 is equal to 6, right? And I want to find the inverse of this. Is it x? No, it'd be the other way. It'd be, I need 6. I'm asked to find the inverse of 6. Pretty much inverse just means that we're swapping the input and our output, right? Like this. So when I'm asking the inverse of 6, what I'm really asking for is this, the 4. That's all I'm really looking for. And then in our graph, or in our actual function, okay, let's do one, I guess. So let's say f of x is equal to, I don't know, x plus 7, right? So we have to replace this in like steps. So f of x is the same thing as y. Y is equal to x plus 7. And then for every x I see here, I'm going to put a y, and for every y I see, I'm going to put an x. So again, this is the whole like flipping like concept of it. So this is x is equal to y plus 7. And now I want to have like our y isolated. So here, what do I do to isolate the y? I have to subtract 7, right? So here it's x minus 7 is equal to y. And that's our inverse. So this is like our, let me write this out again. This is like f of x inverse of x, or is equal to x minus 7. That's pretty much the whole gist of it. This is inverse, okay. Wow, exponential and logarithmic. Okay, so let's do logs first. Logarithmic function. So, logarithmic functions. So let's say I had f of x is equal to log base 2 of 8, let's say. So by itself like this, log base 2 of 8, we can't really do much with it, right? So I would highly advise whenever you see a logarithmic function, if possible, to put it into exponential form because it's a lot easier to interpret it that way. So in this question, let's say I had to evaluate or solve, right? In log form, we can't do much, so let's convert it to exponential. So Professor O calls this the African way, if you guys remember this. So we're going to take our base and put them equal to, so hold up. So it's going to be 2, right, by itself. So I like to imagine that there's an imaginary equals x off to the side. This only applies if there's no already predetermined like equals to whatever over here. So here there is no equals. So I'm going to put an imaginary equals x. So I'm going to take our base and put it to the power of whatever is equal to the right side. So here it's x. So 2 to the x is equal to our actual argument. So here it's 8. So like that. So 2 to the x is equal to 8, right? So do 2 and 8 have some sort of relation in terms of power? Yes, right? Because if I were to write this out, right? So 2 to the power of x is equal to 2 times 2 times 2, or in other words, this is 2 to the third power, right? So 2 to the x is equal to 2 to the 3. So here, since the bases here match up, what I can essentially do is cross them out, and I'm left with just what is on top. So x is equal to 3. So this is an evaluation problem I just did here. But the main thing I wanted to see or teach you guys was how to convert from logarithmic to exponential form like this. So I would highly advise doing that whenever you come across a log. But sometimes it's not that simple. I think week 6 is when we get into the properties. Yeah. So this is like a brief touch up on just functions. Okay, so now we get into graphs, I think. So let's say I had f of x is equal to log base, let's say 2. Then we have like x like that. So in graph form, our log is going to be pretty much, something like that, right? So, and then like this, and this is our asymptote here. So essentially, the domain of log is that log can't be a 0 or negative in the terms of x here. So let me put that out. So x can't be equal to 0 or a negative. So in domain terms, this is going to be, domain is equal to, what is it? It's going to be 0, infinity like that. So 0 non-inclusive to infinity. So it can't be a 0 and it has to be a positive number. This is what it's all saying. So hence why we have an asymptote here, because it's mathematically not possible to have a 0 or a negative in the in our x. So we have a asymptote at here at x equals 0. And then, okay, so now we need our 3 points. So for log, it's a little different than when we normally start off with a like an XY chart, right? So normally our x is going to be like -1, 0, and 1, right? But here it's going to be our y's instead. So like this, like that. So this is really saying that log base 2 of x is equal to -1. How is it possible to get -1 here? Well, so wait, is that what I'm looking for? Yes. So since this is our setup now with our -1, let's turn this into exponential. So we have 2 to the power of -1, right? 2. So we have our base here to the power of whatever's on the right side, so -1, equal to x. So with negative exponents, right? What do we do with negative exponents? It's always going to be 1 over something. It's going to be 1 over whatever this is equal to. So 2 to the power of 1 gives me what? 2. So this is going to be 1 over 2. If that makes any sense. Another way I can write this out is going to be like 1 over the power of 2 to the 1 like that. So I can get rid of the negative. But we get the same thing as just 1/2. So here, x is equal to 1/2. Let's keep going. So we have log base 2 of x is equal to 0. So here, let's do the same thing, exponential form. 2 to the power of 0 gives me 1. Anything to the power of 0 gives me 1. No matter what number goes here, always equal to 1. So here, then we keep going. Log base 2 of x is equal to +1. So again, 2 to the power of 1 gives me 2. So 1/2, -1, 1, 0, and then like 2, 1. These points aren't exact. I kind of drew this graph kind of awkwardly, but just the general shape is that's what a log graph is supposed to look like. Okay, so now we go on to our good old friend, exponential graphs. So let's keep up with the 2's, right? So let's say I had this. F of x is equal to 2 to the x. In graph form, this guy would look like this. So remember how here I had an asymptote at x equals 0? Now here it's going to be y equals 0. Y is equal to 0. And then our graph kind of looks like that. Like that. So let's get our points, right? So x, y. So imagine like log and like exponents are kind of like flipped, sort of, right? This guy's kind of like flipped the other way like this. This guy's flipped like this for log. So we also flip our x and y's. So since log was a kind of a weird one, we did like -1, 0, and 1 on the y side now. Now we're bringing it back to the x's. So we have -1, 0, and 1. So let's put this in. Let's plug this into our thing, right? So we have 2 to the power of -1. Again, right? When we have negative exponents, what happens? It's going to be 1 over whatever. So 2 to the 1. In other words, 1 over 2. 1/2, right? 2 to the power of 0 gives me what? Gives me 1. And then 2 to the power of 1 gives me 2. So again, points aren't exact, but that's the general trend of our exponentials. So log, exponentials. All right, week 6. Kind of a lot going on here. This is post exam 1, so now we're getting into like the main bulk and stuff. So we have logarithmic properties. We have addition and subtraction. We have solving logarithmic equations, exponential equations. Then we get into arc length, the clock question, and then we're converting from radians to degrees. And this is like our litmus test into the trig stuff. So let's get started with our logarithmic properties. So logarithmic properties. So let's say I had f of x is equal to, let's keep it in log base 2. So let's say I had x here, and then I had a plus. Log base 2 of x, let's say plus 4, right? So main thing here is that we see a plus here. So we have log base 2 and log base 2, so they match up. So let's go ahead and put them together now. So when we see a plus here, it really means to multiply. So in order to combine these two, we have to multiply both x and x plus 4. So our setup looks like this. So we have log base 2 x, and I'll leave it in parentheses just for ease, like this. So log base 2 of x times x plus 4. So let's go ahead and do our first term. So we have log base 2 of x squared, and then this times this gives me plus 4x, like that. So our end result here is log base 2 of x squared plus 4x. So now that we did it's called adding, let's do the opposite. Let's do subtracting now. So we have log base 2. Let's do the same problem. I might as well, I guess. So we have log base 2 of x plus 4, but now with a minus. So here, when we saw a plus, it means to multiply. So now with subtraction, what's the opposite of multiplying? We are now dividing, right? So again, so log base 2 of, that's fine, yeah. So the first term here always goes on top. So here our first term was who? X. X all over what? Just this guy, or whatever term is our minus. So x minus 4, and then we leave it at that. No more simplifying, just leave it the way it is. So we covered adding and now subtracting, right? So adding equals to multiplication, subtraction equals to division. So logarithmic properties, and then now let's move on to, solving logarithmic equations. Okay, so I couldn't come up with a problem for the solving part. Also, I made a typo here. This should have been plus, x plus 4. So I'm going to take one off straight up the worksheet. So they gave me here that log base 6 of x plus log base 6 of x plus 5 is equal to 2. Okay, cool. So what do we notice, right? We notice that log base 6 here and here, right? So they're matching log base 6s. And so let's go ahead and look here. What do we have? We have a plus. What does plus mean when we have two log things? We are multiplying, right? So let's write this out again. Log base 6 of x here, and then we have x plus 5, like this, equal to 2. So let's work inward, right? So x, so let's do this. So we have, let me write this out again, log base 6 of what? X times x gives me x squared. X times 5 gives me plus 5x equal to 2. So remember how earlier I told you guys to, when we see log here, like try to convert into exponential form? So let's do that now, right? So log base 6, so we take the 6, put it here, and put them equal to whatever's on the right side, which is here, 2. So 6 squared equal to whatever's inside here, so x squared plus 5x. So 6 squared gives me what? 36 equal to x squared plus 5x. So let's go ahead and bring this guy over here. So 0 is equal to x squared plus 5x minus 36. So minus 36 minus 36. So let's go ahead and take our negative 36 here. And let's find possible factors for 36. So let's do 36, 1. Let's do this guy negative, and negative 1, 36. By 2, we have what? 18, 2, negative 18, negative 2, 18. Let's see. We have 9 and 4. 9, 4, negative 9, 4, negative 4, 9. What else am I missing? 3, I guess. We have 3 and 12. So negative 3, negative 12. 6 and 6. 6 and 6. I think that's about it, I think. So something here has to add up to positive 5. So negative 36 and 1 is negative 35, so not him. This is going to be positive 35. Negative 18 plus 2 gives me negative 16. This is going to be positive 16. Negative 9 plus 4 gives me negative 5. And then negative 4 and 9 gives me positive 5. So it's these two. So let's go ahead and factor these out. So 0 is equal to our x setup again. So we have negative 4. And then we have positive 5, or positive 9, sorry. Like that. Cool. So now let's go ahead and put them equal to 0. So x minus 4 is equal to 0, and then x plus 9 is equal to 0. So x is equal to 4, and then x is equal to negative 9. Cool. So now we got here. But since we solved our x's, now we have to plug them back into here to make sure that they're possible, like they're possible solutions, I guess. So 4 into here, so we have positive. 4 plus 5 gives me 9, so they're both positive. Good. 4 works. Negative 9 into here, we have what? Log base 6 of negative 9. Remember earlier I talked about the log domain and how we can't have a negative like in our solution. So negative 9 goes into here, we have a negative. It can't be possible. So automatically this guy is out. So our own solution here is going to be x is equal to 4. Okay, so another problem I wanted to cover from the worksheet is our exponential equation. I don't know the name for it. So we have 3 to the power of 2x is equal to 1 equal to 5 to the power of 3x. So this is going to be a little ugly one, I'm not going to lie. So our first step here is to do what? It's to establish that these two are ln's. So all we're really going to do is slap on ln to the front of this guy. ln 5 3x. So now that's an ln, what we can do now is to bring the powers down here as a coefficient, and the same thing to 3x. So I want to put this guy in parentheses. So we have 2x minus 1 times ln 3 equal to 3x times ln of 5, like that. So let's start here. So we're going to distribute this 2x to ln 3. So we got 2x times ln of 3. And this negative 1 becomes negative ln of 3, or minus, sorry, equal to 3x ln of 5. So our main goal here is to get all of our x's onto one side, and then we'll work our way out from there. So what we can do here is to trade these two, like ln 3 goes over here, and then 3x comes into here. So, or, actually no, it's like, we can just bring this guy over here. So we have negative ln 3 is equal to 3x ln 5 minus 2x ln of 3. So now that all the x's are on one side, what we can do now is to pretty much factor out one of the x's. So this guy's going to be, it's going to be negative ln 3 equal to x. And then, so what do we get when we factor out an x? We get what? What's left? We have 3 times L, oh my god, I keep running an h. This is going to be ln of 5 minus what? What's left here when we take out an x? We get 2 times ln of 3. I keep running h's. What is going on? Ln of 3. Cool. So now that x is sort of isolated on its own, right? What can we do to completely isolate them now? We can just pretty much divide this whole thing over to here. So I'm going to put the x back over here, just so it's easier. So x is equal to, on the top we have negative ln of 3 all over 3 ln of 5 minus 2 ln of 3. And this is our final answer. It's a bit ugly, but this is it. So I'll probably do another scenario where we don't have to do like the ln stuff, and we'll have our same bases and stuff. I'll do it right now, actually. Why not? Let's say I had 2 to 2x equal to 2 equal to, I don't know, x minus 7. So since the bases here are the same, let's go ahead and cancel out, right? So we're left with 2x equal to x minus 7. So let's bring all the x's on one side. So this guy goes over here. We get what? X is equal to negative 7. That's it. Simple enough, right? So, so now I have no space. So let's go ahead and cover our arc length. Arc length. So the formula goes as follows. S is equal to r times theta, where r, in theta has to be equals to radians, right? So now let's segue into our conversion portion, I guess, right? So how do we convert from degrees to radians? So let's say I had 30 degrees, right? How do we convert 30 degrees into radians? What do we do? So we have times, so if anyone's familiar with stoichiometry from chemistry, right, we have to match our degrees and cancel out to get whatever unit we want, right? So radians is always going to be in pi, in terms of pi, and degrees is always in degrees of degrees, right? So our conversion is going to be pi over 180, where we pretty much flip wherever we need to get whatever unit we want. So if we want radians to be our end result, radians pi has to be on top, and if we want degrees as our end result, then 180 has to go on top. So let's go ahead and multiply, right? So instead of multiplying a whole number to a fraction, this guy just goes to the top. So we're left with what? 30 pi over 180 degrees, and the degrees here cancel out because they're top to bottom. So we have 30 pi over 180. So what we can do here is now pretty much to simplify this 30 and 180. So 18 divided by 3 gives me what? Gives me 6. So this guy can kind of just cancel out, and this guy goes to become 6. So we're left with just pi over 6, right? Or 30 degrees, we already know from the unit circle, right? So pi over 6. So that covers, oh, I didn't even do this yet. So arc length, okay. So imagine we have a circle, right? So I wanted that to, okay, let's say I was given that my radius here is 4. This is 4. And I want to find how much space I cover if my angle that I have here is equal to, I don't know, let's say 60 degrees is here. And I want to find out how much in inches this area is, right? So this outer area. So this is S. So arc length is pretty much just like, imagine a piece of our circumference is the whole thing, right? So let's go ahead and write this out. So we have S equal to r theta, where theta has to be in radians, right? So we have to convert 60 now. 60 in terms of radians. So we have our setup here is now going to be 60 degrees pi over 180 pi, or sorry, 180 degrees. And the degrees cancel out, so we're left with 60 pi over 180. So 18 divided by 6 gives me what? Gives me 3. So this cancels out and becomes 3. So we have pi over 3, right? So s is equal to 4 times what? Pi over 3. Pi over 3. So let's go ahead and multiply it out. So s is equal to 4 pi over 3. And then this would be a calculated question, and then we would get some sort of return on the amount of inches this becomes. But this is pretty much all the setup you need to know. S is equal to r theta. And then just remember that theta has to be in radians. And that's pretty much what I want to cover over in week 6. And then we'll move on to the trig section, starting with week 7. Okay, so week 7, we have SOHCAHTOA, then we have our trig identities, cofunction angles, unit circle, and reference angles. So pretty much all the trig stuff, unit circle, and the whole shebang, right? So let's go ahead and knock out SOHCAHTOA first. So SOHCAHTOA. So sine is equal to what? Sine equal to opposite over hypotenuse. Then we have cosine, which is equal to adjacent over hypotenuse. And then good old friend tan equal to opposite over adjacent. Okay, cool. So remember that SOHCAHTOA only applies to right triangles, right? So they have to have that 90-degree angle somewhere on that triangle. So this only applies to right triangles. It does not apply to, I don't know, regular triangles. Like later down the, when we start working like law of sines and law of cosines, right? That's the whole gist of why we do this, and then what? Oh, trig identities. So trig identities. So most important one, I'm gonna put a little star, is our good old friend sine squared theta plus cosine squared theta equal to 1, right? Knowing this one, I can derive the other two, and this is the most used one anyways. So remember this one, and we'll work things out. So let's go ahead and divide everything here by sine. So every term here divided by sine squared theta. So sine squared theta divided by sine squared theta gives me what? Gives me 1. Right? What's cosine over sine? That's cotangent. Cotangent squared equal to what? 1 over sine is who? Cosecant. Right? So cool. We got our second one. And so now since I divided everything by sine, let's do the other guy, which is cosine. Right? Cosine squared theta. Cool. So sine over cosine is who? It's going to be tan. Tan squared theta. Cosine over cosine gives me 1. And 1 over cosine is who? It's going to be secant. Boom. Easy enough, right? We got our 3. So know this guy, know the other 2. Okay, cool. So SOHCAHTOA, cofunction. Okay. So the whole idea of cofunction is that angles can be converted into other angles. So let's see. But they have to fit a quota. So let's say I had sine of 43 degrees, right? But I want to turn them into a cosine angle. So cosine is a function, or cosine has a relationship with sine, where any angle that's within the 90-degree like range can be converted into another like cosine angle, or vice versa, right? So I'm gonna write this out. 90 minus theta, right? So here, to convert from sine to cosine, what we can do is take 90 minus 43 degrees, and we're left with what? We're left with 47. So this sine 43 degrees is also equivalent to a cosine angle of 47 degrees. This also goes for, let's see, so we have sine, cosine, and then we have tan, tan theta is equal to, this has to be cotangent, 90 minus theta. And then the same goes for secant, where he's equivalent to cosecant 90 minus theta as well. Same thing as this. So they're interchangeable, right? So tan can be equivalent to cotangent 90 minus theta, and then cotangent can be equal to tangent of 90 minus theta, and so on and so forth. So that's cofunction. And then, so I'll erase all this stuff and do unit circle next. And so for post-exam 2, now we have the week 10 stuff. So now we have sine and cosine graphs, and now trig inverse. So let's start with sine graphs. Sine graph. So f of x is equal to sine of x. So I'm looking at just the general shape, right? I'll get into the like the actual graphing details like in a different problem down the line. All right, so graph for a sine looks like it's like a sine wave S. Now this is cosine graph. Cosine graph, so f of x is equal to cosine of x. He starts like this. It's like a U handlebar thing, right? So sine, cosine, what else was there? Trig inverse. Okay, so let's do our big three. So we have sine inverse, we have cosine inverse, and then tan inverse. So inverse is going from coordinates to angles, right? So this is usually like from angles to coordinates, right? Angles to coordinates. Now this is going the other way around. Remember how earlier I said with inverses, it's like swapping the input and the output, right? So this is from angles to coordinates. So now we're going the opposite way from coordinates to angles now. So for sine, the reason why we cut off, or for not just for sine, but like for all the inverse stuff, right? The reason why there's a domain associated to everything, to all the trig stuff, is because without the domains, we pretty much have an infinite answer. Like, it would never stop, right? So mathematicians cut it down into these domains so that we have either a positive or a negative value associated to whatever it is, right? So for sine, our domain is in quadrants 1 and 4. So 1 and 4. So in quadrant 1, it's positive here and it's negative here. So remember though, right? So for sine inverse, it's going to be quadrant 1 to 4, but for our domain, right, it's going to be negative pi over 2 to pi over 2. So the reason being why it's negative pi over 2 and not, like this would be like, what, like 11 pi over 6, 7 pi over 4, all that stuff, right? Is the reason because we always start at angle 0 when we talk about these angles. So if we start at angle 0 and then we go down, we have to go into a negative angles, into the negative territory, right? So it's going to be negative pi over 2 to pi over 2, right? So don't forget that. Cosine. Okay, so cosine, it's going to be positive here and negative here. It's going to be from 0 to pi. 0 to pi. 0 to pi. And the reason why it's not, quadrants 1 to 4, because in quadrants 1 to 4, it's going to be positive in both of them. So we have to go the outer bound now. See, from 0 to pi. And then for tan follows the same like pattern as sine, where it's quadrants 1 and 4, but it's going to be parentheses now instead of the brackets. Because let's take an example at, let's say, pi over 2, right? What's the value of tan or the coordinates at pi over 2? We have what? 0, 1, right? And what's tan again? Tan is going to be sine over cosine, right? So it's going to be 1 over 0. Remember earlier, I said we can't divide by 0, so 1 over 0 is impossible. So hence, we have parentheses instead now, instead of brackets. So remember these, though. These are very important. You're probably getting like 1 or 2 questions on them, honestly. But this is very important for the triangles, though. Those are worth a lot, because those are probably going to be our written portion, or one of them. So we'll get into that whenever we see the problem. Okay, so following up on that, we have week 11. We have trig verifications, trig sum and difference formulas, and double angle formulas. So verifications I kind of want to get out of the way, because this is like, more practice we do, like the better, right? So So I'm gonna take a question off of the in class. So we have cotangent theta over cosecant theta equal to cosine of theta. So with verifications, we always loop back to whatever it's equal to. This is technically our answer, right? We're just trying to get from here to here. So anytime we we're lost or something, just refer to this, and this is our end result, right? So cotangent over cosecant. So who is cotangent? Cotangent is what? It's what over what? It's going to be cosine over sine, all over what? Who's cosecant? Cosecant is 1 over sine. So I don't do keep, change, flip, or whatever you guys do for dividing. I just draw arrows because it's a lot simpler for me. So I'm going to draw arrows to here. So 2 innermost get multiplied and the 2 outermost get multiplied. So this is our numerator and this is our denominator. So numerator becomes what? Numerator is going to be sine times what? Cosine. So sine over cosine, or sine times cosine over what? 1 times sine, or in other words, just sine theta. So sine times cosine over sine. Since these two are being multiplied, they're technically 2 separate entities. So what we can do here is just cross these x's out, and we're left with who? Cosine, right? Cosine here matches with cosine here. Cool, we're done here. Okay, so now, and then the rest of the week 11 stuff is just formula stuff. I'm pretty sure you guys are getting another formula sheet, right? Similar to what we had in exam 3. So, okay, so sum of difference formulas. So let's take sine of a plus beta. So it's going to be sine of a cosine beta plus, because they match the signs, then we have sine of b times cosine of a. So remember, in exam 3, they actually flipped these two. Some people got a little confused about it, but they're the same thing. As long as they have the 2 same components, and it doesn't really matter what order they're in. So they might switch it around just to mess with you guys, but yeah. So okay, that's a, or that's sine a. Let's do sine like that. Damn, I didn't erase that. Okay. So same thing, sine A, cosine B, then minus now, sine B, cosine A, right? So as long as the sign matches, so whatever the original thing had, then it's fine. Right, so that's sine sum and difference. And now let's move on to cosine. So cosine of A plus B, sorry. This is going to be cosine A, cosine B. Oops, this is a minus. Minus sine A, sine B. So pretty much complete opposite of whatever sine plus is doing, right? So we have sine A and they're interchanging sort of. This guy's just cosine A, cosine B all on one side. Then the signs also change as well. And then so moving on to the difference formula, we have same thing, cosine A, cosine B, now minus sine A, sine B. So again, oops, the sign differentiates between cosines. So sum and difference, now what's left? Double angle, okay, double angle. So sine of 2 theta, it gives me 2 sine theta, cosine theta. So these are just multiplied, everything's multiplied together. Then for cosine, there's 3 of them, but we always just use the simplest one, which is going to be cosine squared of theta minus sine squared theta. So just input this and then just square whatever we get from these. And that pretty much covers everything about week 11. A lot of formula work, but again, as long as you know how to use the formulas, we're fine. You don't have to remember the formulas outright, just know how to use them. Cool. Okay, so week 12, we have solving algebraic trig questions in intervals. Then we have the law of sine and law of cosine introduction. Okay, so for the algebraic stuff, I'm doing a really simple one. Let's say, I don't know, 2 sine of x equal to 1, right? So what do we do here? How do we solve this, right? Well, we want to isolate x, so we divide everything by 2. and we get sine of x equal to 1 over 2. So what is this question asking me now? The question is asking me what angles of sine give me 1/2, right? Positive 1/2. So if we think about, all students take calculus, right? So sine is positive in quadrants 1 and 2. So now we need to find out what angles give me 1/2, right? So we know it's going to be 1 and 2. So if we think about it, so x is going to be equal to what? Pi over 6, right? And then who is his equivalent in quadrant 2? It's going to be 5 pi over 6, right? So cool. So this is algebraic. This is pretty simple, right? Just kind of moving over to the 2. But we'll get into like the meat and bones in a later question. Okay, so we had this. What else was there? I had, law of sines. Okay, law of sines. So I'm going to draw like A, B, and C, little a, little b, and little c. Okay, so for law of sines, we always need to have a relationship between an angle and a side, right? So the opposite side. So let's say I had, I don't know, this was like 40. This was equal to, let's say 4. And then I was given 30 for this. And I want to find what b is, right? So law of sines is going to be law or sine of our relationship first. So we have sine 40 over our side, which is 4, equal to sine of whatever I'm trying to find. So I was given 30 degrees over b, right? So we cross multiply here. We have b times sine of 40 degrees equal to 4 times sine of 30 degrees. So now, how do we isolate b by itself? What do? We have to divide everything by sine of 40, right? So b is equal to 4 times the sine of 30 all over the sine of 40 degrees. So this is the law of sines, and the law of cosines is going to be, let's just draw into like another triangle, I guess. So let's follow it up. This is 40 degrees again. This is going to be equal to 4. A is equal to 4. What do I do here? Let's say this was 3. Let's say this is side B. So this is A, B, and C again. So B is equal to 3. And I want to find out what angle B is now. All right, so I'm given an angle and two sides, so SAS, right? So let's do, what do we do here? So we're trying to find B. So it's like B squared is equal to A squared plus, oh wait, no, I already know B. Oops. Not this one then. Let's say I want to find, oh man, that's kind of hard. This is a really bad setup actually. Let's see. Maybe if I want to find C, this would work. So let's see. A squared is equal to B squared plus C squared minus 2BC cosine of C. No, this is A, sorry. Like that. Okay, does that work? No, it doesn't. Okay, scrap that idea, never mind. So edit that out. Okay, so for law of cosines, so law of cosine, so we have our formula. So A squared is equal to B squared plus C squared minus 2BC cosine of A. So this is used to find anything that's not pertaining to law of sines, or if we don't have like a relationship established. So this could work with like a side-side angle. So if I draw a generic triangle, let's say I was given that, so let's do A, B, and C again. So A is equal to 2, B equal to 3, and C is equal to 4, right? And I want to find what angle A is. So we saw something similar to this in exam 3, right? It was like a really big question, like for the written one. So, right, so we know the formula and we want to find what angle A is. So we know all the sides, so let's go and plug it in. So A squared is equal to 4. 4 is equal to 3 squared, which is 9, plus 4 squared is 16, minus 2 times 4 times 3 cosine of A. Right, so let's go and do this out. So we have 4 is equal to 9 plus 16, so 25, minus, what is this, 12, 24? 24 cosine of A. And so now let's go ahead and move this guy over. So 4 minus 25 gives me negative 21. Negative 21 is equal to negative 24 times cosine of A. How do we isolate cosine of A now? We have to divide everything by negative 24 here because this negative 24 is being multiplied to cosine of A. So negative 24, negative 24. So we have cosine of A is equal to 21 over 24 because the negatives cancel out, right? And this would return some sort of angle in the calculator. So yeah. Okay, so now we have week 14. We have converting polar points into rectangular or Cartesian coordinates and vice versa. And then we touch up on ellipse and hyperbolas. So polar points, so polar points to rectangular. So polar points is going to be from r comma theta, and then rectangular is our common, x, y coordinates, right? So how do we convert these two? So what do we do? X is going to be r cosine of theta, and then y is going to be r sine of theta. Oh, I didn't put parentheses for this one. Let's match that, right? So to convert is just literally just plugging in whatever values. So let's say I had, I don't know, 2 comma pi over 6, right? Something simple of unit circle, right? So x is equal to 2 cosine of pi over 6, right? So what's cosine of pi over 6? We get what? 2, it's going to be a comma, or it's going to be 3 over 2. So x is going to be equal to 2 times this over 2. These two kind of just cancel out, so x is equal to radical 3. Okay, so now let's do y. So y is equal to what? 2 times sine of pi over 6. So sine of pi over 6 gives me what? It's going to give me 1 over 2. So 2 times 1 over 2. 2's cancel out. Y is equal to just 1. Cool. So our, 2 comma pi over 6 becomes just radical 3 comma 1. Cool. So polar to rectangular, and then rectangular to, what is this thing called? Polar points. Jeez. So we have, this is not r squared. Sorry, this is c squared. But c squared and r are kind of like, well, r and c are kind of like the same thing. So we have c squared equal to square root 3 squared plus 1 squared. So c squared is equal to, so radical 3 squared, it gives me just 3. 1 squared gives me 1. So c squared is equal to 4 square root both sides. C is equal to plus or minus, oops, not 4, 2. But, right, C and R are pretty much the same thing, right? So C is just like the longest side, or in a triangle, right? C is our hypotenuse, and R is also the same thing. But we know that R and hypotenuse has to be positive because we cannot have a negative distance. So here it's going to be positive. So C is equal to 2. So match up to what I had here. And then to find the, oh, how do I find this? Oh, right, so this is a triangle. I forgot to do that. Oh, wait, no, oops. Let's rewrite that again. So in the point square root 3 comma 1, right? So let's look at the polarity of each coordinate. So radical 3 is positive, and so is 1. So in a unit circle like standard, this is going to be a quadrant 1 triangle because it's both positive coordinates. So this is going to be radical 3, and my y is going to be 1. I just found this was 2. So pretty much this is my setup. So now I can do whatever like trig functions I can do. I usually go with like I stay away from the radicals. So let's do opposite and hypotenuse. So who is that going to be when we do opposite and hypotenuse? It's going to be sine. So our sine theta is going to be equal to 1 over 2, right? So let's do the inverse now. Well, not inverse. Is it, would it be inverse? I think it would be. So sine inverse of 1/2 gives me theta, right? So now the angle, it's asking me what angle gives me a positive value of 1/2, and it's going to be in quadrant 1 because it's positive up here. So our theta is going to be positive pi over 6. So matching it up to here, we have pi over 6 and 2, right? Like that. So this is converting polar to Cartesian. And now let's do ellipses and hyperbolas. Okay. So ellipses. So ellipses look like it's like an oval or like a football kind of, right? It's like a little like that. And then so this is a horizontal, and then for this one it's like a upright oval. This is a vertical. So this is going to be an x major, where vertices are lying on the x-axis, and this is going to be our y major, where our coordinate or our vertices lie on the y-axis, right? So pretty much this is going to be where, okay, so what's the generic formula again? This is going to be x squared over, what is it, a squared? Oh, I think it's minus. No, it has to be plus, right? Oh my god, I forgot. Oops, scratch that. Okay, so the generic formula of an ellipse is going to be x squared over a squared plus y squared over b squared equal to 1. So pretty much an x major happens when the biggest radius, I guess, would be on A, and then y major would be like B is the bigger. So like, if this makes any sense, right? But pretty much they would tell you either on the graph or in words where our vertices lie. Okay, so let's say, for example, they gave me an ellipse, right? So let's say it was just a horizontal ellipse. And they gave me that this point is going to be at 4, 0, and that this one is going to be at, I don't know, like 0, -2, right? And it asked me to find what the equation of this ellipse is. So I know that this is going to be horizontal because why? 4 is bigger than 2, right? So this guy is going to be x squared over 4 squared plus y squared over -2 squared equal to 1. Right, so let's do the math. So x squared over what? X squared over 4 squared, which is 16. Y squared over 2 squared, which is 4, equal to 1. So this is our equation. I guess I'll do it here. So now let's move on to hyperbolas. Hyperbolas. Okay, so hyperbolas usually look like, I'm going to do it up here, I guess. So again, we have our grid, and then we'll have our little box, and then we have our lines that drive, oh my god, I missed that, from corner to corner through the center. So imagine this guy went through the center, right? And then now, let's say you start from here. It's going to go out to here, like that. Like so. And I'm asked to find what the equation is. So our generic formula is going to be x squared over a squared minus y squared over b squared equal to 1, right? So let's say I gave you this point was, let's say this was at y equals 4, and that this guy lies at x is equal to 3, right? So I'm making a box with 4 and 3. So this guy, since y is bigger here, y is actually going to go in the front. So it's going to be y squared over what? Over 4 squared, which is 16, minus what? X squared over 3 squared, which is 9, equal to 1. So they would say this in some sort of like vertices and like focus thing again, right? And we have to figure out what A, B, and C is. But if they give you the graph like this, Like you can figure it out from just like linking the grid and like where the box aligns with. And so finally, we have week 15, right? So this would be this week. So we have n-term algorithms and we have summation and factorials. So n-term algorithms are just going to be, it's a formula again, right? So this is going to be, what do you call this? I think arithmetic sequence. I'm pretty sure this is what they're called. I'm not too sure. an is equal to a1 plus n minus 1 times d. So this is saying this is like our final term, or like the change, right? This is our initial point. This is like our n term minus 1 times the difference. So you would be given some sort of like thing. So let's say like, okay, let's say a1 is equal to 1, and let's say an is equal to 10. So we need to find the difference between these two, right? So 10 minus 1 gives me what? 10 minus 1 equals to 9. So d is equal to 9. And now I need to find out what term this is. Does that make sense? I think it does. So let's plug this in. So we have 10 is equal to 1 plus n minus 1. And my difference was 9. So let's go ahead and do that. So 10 is equal to 1 plus what? To distribute, we have 9n minus 9, like that. So let's combine these two. So 10 is equal to 9n minus 8. So move this guy over. 18 is equal to 9n. So now let's go ahead and distribute, or not distribute, oh my god. Isolate the n, so we're going to divide by 9. So we have 2 is equal to n. So we're finding what number this was in the sequence, I guess. Yeah, so that's arithmetic. Okay, so summation. Summation looks like this, I think. So this would have the initial and our final point. So let's say this was like 3 and 1. Let's make things simple, right? Let's say my thing was, I don't know, x plus 1, right? Summation just says we have our initial and our final point, and we need to find everything from like our term 1 to 3, so 1, 2, and 3, everything in between, and we have to add them all up. So let's start at 1, right? So we plug in 1 to here, we get what? 1 plus 1, which is a 2. Cool. So now we move on to the next term, right? So 1, 1, 2, and 3. So we did 1, now let's move on to 2. 2 plus 1 gives me 3, right? And then 3 plus 1 gives me 4. Now add all these up, so we have what? 4 plus 3, 7, plus 2, 9. So our final thing from a summation of 1 to 3 from this is 9. Okay, that's summation. So now let's move on to factorial. I need to write these out. I'm gonna forget. Summation, and then we have factorial. Factorial, okay, so factorial is gonna be exclamation mark. So let's do 3 exclamation mark. All right, so this means that it's gonna be 3 times 2 times 1. This is gonna, the exclamation mark means like it's gonna be every number like after whatever this is up until 1. So this could go like, you know, any number, just it goes backwards all the way to this, and we can multiply everything. So 3 times 2 is 6 times 1 is just 6, so equal to 6. So 3 factorial is 3 times 2 times 1. So another one we could do like, I mean they're pretty repetitive, but like let's do like 5 factorial, right? So like 5 times 4 times 3 times 2 times 1, right? So 5 times 4, 20 times 3, 60, 60 times 2, 120 times 1. So this 5 factorial is equal to 120. Things like this, right? And that about wraps up pretty much everything we've covered in this course, right? And now we'll do like some more practice problems. I'll skim through the final review, and I'll pull the questions off my exams and stuff. But yeah, best of luck. Okay, so since we did a recap of everything we've done so far in this class, I came up with like 10 things to remember, kind of like just like help you guys out, right? So I call it the 10 commandments to pass this class. So number 1, isolate x, right? Pretty general. If we're solving for x, we need to isolate them in whatever way we need to do, is like factoring. So factoring, if we're solving for x, we have to equal to 0, by the way. So, you know, do whatever you need to do. Recognizing difference of squares. So I'll do an example, right? So let's say I had like x squared minus 4, right? we need to know that this is like x plus 2 and x minus 2 factored like this, because 4 is a square, right? So 1, 2, okay, so let's do 1 squared gives me 1, 2 squared is 4, 3 squared, 9, et cetera, et cetera, et cetera, right? So this goes on infinitely, but remember, right, it's x squared minus whatever square becomes this. Just remember that, right? So 2, domain and asymptotes. Remember that domain is always associated to our, our denominator and square roots, logarithms and stuff, right? And asymptotes follow along with whatever points our domain falls at. 3 is logarithms and exponential functions. Remember, like if we need to add, subtract, or whatever, like it's going to multiply or divide, respective thing, and always convert from log to exponentials if we can, right? It makes things solving like our equations a lot easier. All right, number 4 is unit circle and all students take calculus. So for unit circle, I know what the unit circle looks like, like by heart, right? But to solve things, I use this little I guess kind of guide. I don't really know what you call this. Professor O kind of covered it briefly, but he didn't explain how to use it. So I do sine 1, 2, 3, and then cosine of 3, 2, 1. So imagine this is like a little chart. All right, so I have, I need to do another row here. So imagine this, like that. So I'll put angle here. So imagine this is quadrant 1, right? So we have pi over 6, pi over 4, and then pi over 3. Oops. So let's say I wanted to find cosine of pi over 3, right? So pi over 3. Cosine is what? What's my numerator? It's going to be 1, right? So cosine of pi over 3 is going to be equal to 1 over 2. So everything here is going to be square rooted and over 2. Right, so square root of 1 is just 1, so just 1/2, right? This is what I use, just to know unit circle off the top of my head. I just use this, sine 1, 2, 3, and it goes in order of pi over 6, pi over 4, pi over 3, right? So if I draw this out, right, it's going to be pi over 6, pi over 4, pi over 3. So this is going to be what? 3, 1, 2, 2, and then 1, 3, like that. All right, so cosine, comma sine, and this is my general rule of finding out what the values are. Okay. Oh, and then all students take calculus, right? So all students take calculus, right? This stands for all. This is sine, tan, and then cosine, right? So these are positive, positive. This is negative, positive, negative, negative, and then positive, negative, right? So all students take calculus. Okay. Number 5 is converting degrees to radians and vice versa, right? So our pi over 180, very important for when it comes to, I guess, unit circle, right? When we're solving the double angle formulas and stuff, that's pretty important, sort of. But mostly the clock question, what else? What do we got? There's more problems, right? Just know them, right? Number 6 is gonna be SOHCAHTOA. Only applies to right angles, again, right? Remember what SOHCAHTOA means, right? Each thing. Number 7, Trig Identities, right? I taught the shortcut, knowing sine squared theta plus cosine squared theta equal to 1, and derive the other 2. Number 8 is going to be trig inverse domains, right? So every trig function has a domain associated with it. I just draw the little grid and draw the arrows, right? Sine is, what is it? Sine inverse has a domain in, what's it called? Quadrant 1 and quadrant 4, right? From negative pi over 2 to pi over 2, and so on and so forth. Number 9 is going to be ellipse and hyperbolas. Remember what the formula is for each one of them, right? So ellipse is going to be, this is a plus, and hyperbola is a minus. That's like a general thing. And number 10, please, for the love of God, do not leave anything blank. If it's a multiple choice question, take your chances, just pick 1 out of the 4 or 1 of the 5, whatever it is. Please do not leave anything blank. I'm sick and tired of seeing people leave things blank. Please. If it's a written portion, just try your best, right? If you get stuck somewhere and you don't know what to do, just stare at the formula sheet, and if something clicks, work on it, right? If not, just do something. Please don't leave anything blank. Please. And yeah, that about wraps up the 10 commandments. And so now let's get started on some practice problems. Okay, so I'm going to go in order as they appear on the final exam review. So first off, I have number 2 here. It says to solve the logarithmic equation, be sure to reject any value that is not in the domain of the original logarithmic expressions. So they gave me this, log base 4 of x minus 4 plus log base 4 of x minus 10 equal to 2. So we notice what? That log base 4, right? So that means that we can combine them some sort of way. We see a plus here, so plus means what? When it comes to logs, it becomes multiplication, right? So let's go to do that. So we have log base 4 of x minus 4 times x minus 10 equal to 2. So let's go ahead and work this out in the middle. So we have log base 4 of what? So it's FOIL. So first term gives me x squared. Outer gives me minus 10x. Inner gives me minus 4x. And then outer, or no, what is it? Last, sorry. So negative 4 times negative 10 gives me plus 40 equal to 2. So we see log base 4 of this whole thing equal to 2. Let's turn this log into exponential, right? How do we do that again? We take our base and put them equal to, or not to the power of whatever is equal to the right side, which is 2, equal to this whole thing, x squared minus 10, actually, oops, not 10x. So let's combine these two. It becomes 14x. 14x plus 40, right? Cool. So let's do this side. 16 equal to x squared minus 14x plus 40. 40 minus 16 gives me 24. So x squared is equal to 0 minus 14x plus 24. So now let's find factors of 24. 24, so let's do 24 and 1, and negative 24 and 1. Or, oops, like that. So what else we got? Negative 12 and 2. Negative 12, negative 2 gives me 14. So it's these. So 0 is equal to x times x. Cool. So x minus 12 and then x minus 2. Cool. So let's go ahead and set them equal to 0. X minus 12 equal to 0. X equals to 12. X minus 2 equal to 0. X is equal to 2. So now we got our 2 answers. Now let's plug them back into our formula and see what we get. 12 minus 4 gives me 8, positive. Okay. 12 minus 10 gives me 2, both positive. 12 is good. 2 minus 4 gives me negative 2. Off rip, this guy's no good. So 2 is out of the equation, and 12 is our only answer here. Cool. So that's number 2. What else we got? I have enough space for 3. Okay, so 3 gives me that find the domain of the function g of x. G of x is equal to radical x minus 1 on top over x minus 9. Okay, so find the domain, right? So I said domain is always associated to the bottom, but in special cases, like the radical on top, we have to also take account of him. So let's take our bottom first. So we have x minus 9 equal to 0. X is equal to 9. Now let's take the top. So x minus 1 has to be greater than or equal to 0. So x has to be greater than or equal to 1. Right, because if you plug in 1 to here, we get square root of 0, which is just 0. So we get this. Now let's do our numbered line. So we have 9, and then we have 1. Wait, no, other way around. Oops. So we have 1, and then we have 9. So 9 is our asymptote. It cannot be. So now, x has to be greater than 1, so it has to be here, but it can't be 9, and it goes further. So this is okay, and this is okay, and it can't be here. So our domain is going to look like this. Domain is going to be bracket 1 because it's included here, bracket 1 to 9, parentheses because 9 isn't included here. Then we have union of 9 comma to infinity because 9 is not included. So we stop here and we pick back up, and the next one going onward. Domain looks like this. So for number 5, we have a triangle. So let me try my best here and simulate this triangle. So this is point C. Wow, that's a triangle, all right? So we got A, 115 degrees, and here at B is 30 degrees. They gave me A, C, and then B is equal to 7. So solve the triangle below. So we need to find angle C and sides A and C. So let's start off with our angle. So to find our angle, a triangle has to be equal to 180. And they gave me two angles, so 115 and 30. So this is going to be 180 minus 145. So this gives me 35. So C is equal to 35. So now let's do law of sines to find side A. So I have a relationship between side B and angle B. So we have sine of 30 degrees over side B, which is 7, equal to sine of angle A, which is 115, over side A. So cross multiply, we get A sine of 30 degrees equal to 7 sine of 115, right? So just slap on to the front of it, right? So now let's isolate A. So to isolate A, we just divide by sine 30. So A is equal to 7 sine of 115 over sine of 30 degrees. Cool. So now that we just found side A, let's find side C now. So I always like to stick with whatever relationship they gave me. So sine B over B, right? So sine of 30 degrees over side B, which is 7, equal to now our new angle we found was C. So equal to sine of 35 degrees over side C. So again, cross multiply. We get sine, or C sine of 30 degrees equal to 7 sine of 35 degrees. Isolate C, divide everything by 30. So C is equal to 7 sine of 35 degrees over sine of 30 degrees. That's solving a triangle. And so for number 10, they gave me that find the vertices and locate the foci for the hyperbola. So this is going to be question 10. They gave me that y squared over 25 minus x squared over 100 equal to 1. So find the vertices, right? So who's bigger, 25 or 100? It's going to be 100, right? So who's 100 under? It's going to be x. So what's 100 squared? 100 squared is just 10, right? So plus or minus 10 is going to be our vertices. So if it's going to be our x's, right, x is equal to 10, that means our vertices are going to be at 10, 0, and at negative 10, 0, because we have to go both ways, because square root 10, or square root 100, which gives me plus or minus 10. So vertices are at 10, 0, and negative 10, 0. And now foci. So foci is going to be c squared is equal to a squared plus b squared, right? So a and b. So we have c is equal to 25 plus 100. So c squared is equal to 125 squared. So c, if we square root this, it's going to be c is equal to plus or minus. Okay, so we can either leave it as 125, or we can do, it's going to be square root 25 times 5. In other words, this is going to be plus or minus 5 square root 5, like that. So our foci will be plus or minus this. So this is going to be a x major, what's it called? A horizontal hyperbola. So the coordinates for this is going to be 5 square root 5, 0, and then it's going to be negative 5 square root 5, 0, because they have to follow along with the vertices. Okay, that's number 10. Then they gave me number 13, which is graph the ellipse and locate the foci given, 4x squared equal to 64 minus 16y squared. So, okay, so they moved this guy over here for some reason, so let's move him back over. So we have 4x squared plus 16y squared equal to 64. Now, remember our standard ellipse thing? It looks like this. It's like x squared over a squared plus y squared, over b squared equal to 1, right? So we have to get the 64 equal to 1. So we do that by, by dividing everything by 64. So we have 4x squared over 64 plus 16y squared over 64 equal to 64 over 64. So 4 divided by 64, or vice versa, that's going to give me, oh boy, I want to say 16. Should be 16. So it's going to be x squared over 16 plus 16 divided by 64, or 64 divided by 64. Well, 64 divided by 16, sorry. This would be y squared over, I want to say 4, and this is equal to 1 now. So now that we have this set up close to our like generic formula, right? Now, how do we find the, what is it called? Graph the ellipse and look at the foci. Okay, so graph this out. So 16 is bigger than 4, so that means this is a horizontal ellipse. Let's do that. Right, 16 squared, or square root of 16 gives me plus or minus 4, and this gives me plus or minus 2, because square root 4 gives me plus or minus 2. So 4 and 2. So let's say this is 4, 4 comma 0, 4 comma 0. And this is going to go up 2 units, so like that. So this coordinate, or my vertices, so let's write that out. Vertices are going to be vertices are going to be at -4 comma 0 and at 4 comma 0. Now to find foci. So foci is going to be a formula. So it's going to be c squared is equal to, oh boy, let's see, it should be a squared minus b squared, I want to say. Right? A squared in front, b squared like this. So c squared is equal to 16 minus 4. 16 minus 4, c squared is equal to 12. Square both sides. C is plus or minus radical 12. If you want to simplify this even further, this is going to be square root 4 times square root 3. So 4, square root 4 is 2. So c is going to be plus or minus 2 radical 3. It's like that. So foci should be like somewhere here, something like that. So number 15 gives me the complete identity of, so 15, it gave me sine squared x plus sine squared x times cotangent squared x equal to what? Okay, so I see that there's a sine squared x here, so let's factor them out and see what we get. So we get a sine squared x on the outside equals, not equals to. Big parentheses, we have a 1 here because we factored them out, plus what? Plus cotangent squared x. So cotangent squared x is a, what do you call it? A trig identity, right? So put this down. So sine squared x plus cosine squared x equal to 1. So how do we find cotangent? Cotangent is what? Cosine over sine. So let's divide everything by sine here. By sine, by sine, by sine. So sine squared over sine squared gives me 1. This guy is cotangent squared. And 1 over sine is cosecant. Right? It's like that. So let's replace this with now just cosecant. So we have sine squared theta on the outside of, let's put a c here, cosecant squared theta. So sine is just sine times what's called cosecant, right? Cosecant, let's put them into sine terms. So we have sine squared on the outside times 1 over sine squared theta, like that, right? So sine goes up here and just cancels out anyways, or we just cancel out here. So my identity here is equal to just simply 1. Okay, and then for number 16 is a difference quotient. Ooh, let's go. 16 gives me that they want to find the difference quotient of this. f of x is equal to x squared plus 9x minus 2. So if you guys remember the, what's it called, difference quotient formula I put out earlier, right? So it's going to be f of x plus h minus f of x all over h. So I go step by step. So I want to do this part first. So let's replace this whole thing, right, with now x plus h. So for every x I see, I'm going to put x plus h, right? So x here becomes x plus h squared plus 9x plus h minus 2. So let's work it out. So this guy gives me what? This guy's going to give me x squared. So FOIL it out, and we get 2xh plus h squared, like that. This guy becomes what? I'll put him in the parentheses, 9x times 9h minus 2. Okay, good. So now let's combine like terms, right, if we can. Can we? No, we can't. So let's leave it the way it is now, and now let's move on to this part. So now minus f of x, right? So we have x squared plus 2xh plus h squared plus 9x plus 9h minus 2 minus what? Minus this whole thing. So we have x squared plus 9x minus 2. So let's go ahead and distribute the negative, right? Or can we cancel anything out here? No, it's probably better off I just distribute this negative now. So I'm going to rewrite this out without parentheses this time, just so it's easier. 9x plus 9h minus 2. Right, now we have minus x squared minus 9x, and now plus 2. So let's start with x squared. Can we cancel anything out with him? Yes, we can, right? 9x, we have a 9x here, or negative 9x, sorry. And a positive 9x. We have negative 2 and a positive 2. These two cancel out. So now we're left with this. Now let's move on to the last part, which is dividing everything by h. So we're left with not negative, my God, 2xh plus h squared plus 9h all over h. So this guy gets has to divide it by everything, right? So this guy goes bye-bye, squared goes bye-bye, and this guy goes bye-bye. So we're left with just 2x plus h plus 9. And this is our difference quotient. Okay, number 17. Use properties of logarithms to expand the logarithmic expression as much as possible. Where possible, evaluate logarithmic expressions without using a calculator. So I have number 17. They gave me big log base 7 of this whole thing to the 4 root of x to the 5 times y all over 49. Okay, cool. So let's start by separating both top and bottom, right? So let's go ahead and write this out as log base 7 of the 4 root of x to the 5 times y minus this guy over 49. Okay, oh my God. Okay, so what can we do here? What can we do? So let's start by separating him too. We have log base 7 of cube root, not cube root, sorry, the 4 root, I don't really know. So what's happening here? X to the 5 is being multiplied to y, so that means it's going to be a plus, right? Plus log base 7 of y. Now let's put it back in. Oh, I forgot to put a log up here, sorry. Log base 7 of this guy to the 49. Okay, so now let's convert this. Oh, I forgot to put this into this guy as well. Let's turn this, the cube root, no, oh my God, I keep calling cube root, the 4 root into a power, sorry. So this guy is equal to 1 over 4. So we have log base 7 of like pretty much x to the 5 to the power of 1 over 4. Right, so let's get rid of that cube root, or oh my God, I keep calling cube root. The 4 root, because he's getting a little annoying, right? So we have y to the 1 over 4 minus log base 7 of 49 to the power of 1 over 4. Good. So now what? Let's bring this guy up here. So the 1 over 4 kind of gets like added to the 5, right? The 5 just goes on top. It's 5 over 4. It should have been 5 over 4 in the start. I probably should have done that. So, and then this guy just goes to the front. This guy also goes to the front. So we have 5 over 4 of log base 7 of x now. This guy, I'll just do that now. This should have been 5, and the x stays inside. And this guy, bring him forward. So 1/4 log base 7 of y. Should I bother putting parentheses? I'll do away with that. Now bring him also to the front. 1/4 log base 7 of 49. Okay, so this guy we can't do anything further. Same with the y, right? So x and y stay the same. But it's 49 and 7, right? Can we do something with 7 and 49? They have a relationship in some sort of way, like powers? Yes, right. So 49 is just 7 squared. So let's reduce this into 2 now. So it's going to be 5 over 4 log base 7 of x plus 1/4 log base 7 of y minus, so if we reduce this into 2, right, it's just, well, this whole thing here becomes 2. So this 2 times 1/4 gives me what? 2/4 or 1/2. So our final answer is just going to be this, minus 1/2. Okay, so that's 17. And I have space for another one. So this is going to be question 27 now. 27, okay, so a building 260 feet tall casts a 100-foot long shadow. So this is going to be the thing like my horizontal side. If a person looks down from the top of the building, what is the measure of the angle between the end of the shadow and the vertical side of the building? So let's go and draw that out. So I have a standard right triangle here. Okay, so a building here. Let's just pretend that's a building. This is going to be 260 feet tall. It casts a 100-foot long shadow, so 100 feet. If a person looks down from the top of the building, so here, what is the measure of the angle between the end of the shadow and the vertical side of the building? Let's assume the person's eyes are level with the top of the building. Okay, good. So in relation to this theta, right, what sides are these, right? So from here to here, it's going to be my opposite, and this is going to be my adjacent. So if we think back to SOHCAHTOA, right? SOHCAHTOA, right? Who has my opposite and my adjacent? It's our friend tan, right? So if we take tan of theta is equal to opposite, which is 100, over my adjacent, which is 260, what do I get, right? I'm going to get this. So now, to get my angle, I'm going to do the inverse to get the angle. So tan inverse of these two switch, 100 over 260, is equal to theta. And this is our angle. This is a calculator question, but if you were to be asked this on the exam, this should be your final answer. Question 36 gives me that solve this. So 36, solve x times x plus 3 times 5 minus x is greater than or equal to 0. So what this is really asking me is like what zones are like are positive or equal to 0. Right? So let's put everything equal to 0. X equal to 0, x plus 3 equal to 0, and 5 minus x equal to 0. X equals 0 already in simplest form. X is equal to negative 3 here. Move the x over, x is equal to positive 5. Okay, so this is a number line question, if you guys remember this. So the most negative person here is negative 3. Next most negative one is 0, and then 5 finally. So now we're asked to find where is it greater than or equal to 0. So let's number test this. So we can do negative 4 here, and let's do negative 1. This could be 1, and this could be 6. So I'm just testing numbers around these zones to see if my answer is negative or positive. So negative 4, so I have negative on the outside. Negative 4 plus 3 gives me negative again. And then 5 minus negative 4 gives me a positive. So negative times negative gives me a positive times a positive, positive. Negative 1 on the outside. Negative 1 plus 3 gives me positive 2. And then 5 minus negative 1 gives me a positive again. So negative times positive gives me negative. Negative times positive again, negative. 1. Okay, so I got a positive on the outside. 1 plus 4, another positive. And then 5 minus 1, another positive. So positives all around, positive. 6. 6 is a positive on the outside. 6 plus 3, 9. And then 5 minus 6 is a negative. So positive times positive, positive. Positive times negative, negative. Boom. So our setup here is going to become this. So my only positives here are between what? Between negative infinity to negative 3, included here because why? If negative 3 here becomes a 0 here, 0 times anything gives me a 0, right? So hence, this is included because it's asking whether it's greater than or equal to 0. So negative 3, union what? What's my next zone that's positive? It's going to be from 0 to 5, right? So these are also included because the same reasoning as negative 3, like that. Okay, so my answer here should be from negative infinity to negative 3, bracket, union, bracket 0, comma 5, and bracket. Okay, and so now, I might as well do the next graph as well. So 37, use transformations to graph f of x is equal to negative 2, x plus 4, minus 3. So determine the domain range and find the equation of the horizontal asymptote. Plot all these 3 points in the graph of the basic function and use them to perform transformations. Do one transformation at a time and write the equation for each basic function, or each function, sorry. So my basic function here is what? Basic f of x is equal to, it's going to be 2 to the power of x, right? So on a graph, let's do our xy table here. So again, we always want a negative, a 0, and a 1, right? Or a positive, doesn't really matter. Right, so 2 to the power of negative 1 gives me what? It's going to be 1 over 2 to the power of 1, which gives me 2. So 1 over 2 is my final result. 2 to the power of 0 is going to be 1. 2 to the power of 1 gives me 2. So negative 1, 1/2, 0, 1, and then 1, 2. Connect the dots. Wow, I missed every single dot. That's crazy. And then here my asymptote is going to be here. At y equals 0 is my horizontal asymptote. Because why? Because no matter how negative we go, it's always going to be 1 over something. And we can't have 1 over 0. Hence, the x-axis is never going to be touched. It's always going to be 1 over something. Moving on to the first transformation. So looking at this, we have what? We have to start here, within the parentheses, right? So first transformation is going to be what? What's happening here? What does x plus 4 mean in this context, right? We're moving 40 units where? To the left. We're pretty much doing the opposite of whatever's in the parentheses. So 40 units left. My function is going to look like this. F of x is equal to 2 to the power of x plus 4. Okay, so now let's go ahead and draw my little graph and draw xy tables. So in this context, right, we're using 40 units left. So we're moving 40 units left. So when we talk about left and right, we're going to be moving our x's. So the y's stay the same. Let's go ahead and jot them down. 1/2, 0, and 1. Right, and what's happening to the x's again? We're moving 4 to the left. So minus 4. So negative 1 minus 4 gives me negative 5. Negative 5, 0 minus 4 gives me negative 4. And 1 minus 4 gives me negative 3. So negative 5, 1/2, negative 4, 0. Oh, oops. This should have been 1, comma 2. That's wrong. Okay, so negative 5, 1/2, negative 4, 1, and then negative 3, 2. Connect the dots. Yeah, I didn't miss this time. Let's go. And horizontal asymptote stays the same because we're not moving left and right with the asymptote. Okay, so now, second transformation. So let's move outward of the parentheses, right? So we did this, now let's move outward to here. What does that negative mean? What's happening here? It's going to be a reflection, right? But over what, though? So since this negative is on the very outside, right, the very first thing we see, right, this is going to be a reflection over the x-axis because this negative, right, is going to be applied to our y values. So reflection over x-axis. So here, my function is going to look like this. F of x is equal to negative 2x plus 4. So this is a reflection over the x-axis, so my y values are being affected. So let's transfer over our x values. So x comma y table. So let's keep our x's, negative 5, negative 4, and negative 3. I'm going to go back to here. I'm just going to put a negative in front of everything here. So 1/2 becomes negative 1/2. 1 becomes negative 1, and 2 becomes negative 2. So negative 5, negative 1/2, negative 4, negative 1, and negative 3, negative 2. Connect the dots like that. And asymptote stays the same because negative 0 is just 0, right? And so now my final transformation is going to be what? Transformation. So we did the parentheses, we did the front. Now let's move on to our vertical shift, right? Where are we going with this negative 3? It's 3 units to down, right? So f of x is going to be equal to negative 2 to the x plus 4 minus 3. So the same thing as this, right? Now, draw the grid, xy table. So what's happening when we're moving 3 units down? Who's changing, x or y's? It's going to be my y's, right? So again, go back to here. I'm going to transfer over the x's again. So we have negative 3, negative 4. Oops, this is negative 5. Damn, I can't even read my own handwriting. Crazy. Cool. So what's happening with these units, though? We're moving 3 units down, so that means minus 3, right? So negative 1/2 minus 3, I get negative 3 1/2. Negative 1 minus 3 gives me negative 4. And negative 2 minus 3 gives me negative 5. So negative 5, negative 3 1/2, negative 4, negative 4, and then negative 3 is going to be negative 5. Something like that. This goes like that, like this. And so now our good old friend horizontal asymptote also moves along with this vertical shift. So he's going to be around here, where y is equal to negative 3, because 0 minus 3. Oh, and then put the thing in here. Y equals 0, and y equals 0. So 0 minus 3, negative 3. Hence, horizontal asymptote is at 0, or it's at y equals negative 3. Okay, and so for the last question I wanted to cover from the review is question 42. So this follows along with the zero multiplicity chart we did earlier. So they gave me analyze and graph the function. F of x is equal to negative x squared of x minus 1 times x plus 3 as follows. So A, determine the end behavior. So end behavior is pretty much a, what do you call it? It's the degree of everything added up. So we have 2, 1, and 1. So 2 plus 1, 1, 1 gives me 4. So we have a negative even. So negative even. So negative even looks like this. This can be like a downwards parabola. So we're going to start negative and we're going to end negative. So end behavior is going to be end behavior is going to be like negative, negative. Okay, find the power function that the graph of f resembles for large values of x. What does that mean? I'm just gonna put like negative x squared or something. I don't know what that means. Okay, so this was A. B, find the x-intercepts. Okay, so let's pretty much put everything equal to 0. So negative x squared equal to 0. So x is equal to 0. X minus 1 equal to 0. move this guy over, x is equal to 1, and then x plus 3 equal to 0, x is equal to negative 3. So these are all our x-intercepts. So in coordinate form, this would be like 0, 0, 1, comma 0, and negative 3, comma 0. So C, determine whether the graph crosses or touches the x-axis at each intercept. So this is going to be our 0 and multiplicity, and then touch or cross. So 0 at 0, then we have 1, and then negative 3. So 0 came from negative x squared, so his multiplicity is going to be 2. Touch across, this is going to be a touch. At 1, this came from x minus 1, so multiplicity was 1. This is going to be a, what's it called, odd. This is going to cross. Negative 3 came from x plus 3. This guy was also multiplicity of 1, so this is also going to be a cross. Okay, and then now, so A, B, C. Now D is going to be graph. So I'm going to go ahead and draw just a simple graph. So, okay, so what do I have? So negative 3 was here. Let's say it was like here. Negative 3, 0, and then at 1. So at negative 3, it crossed. So we know for M behavior that it starts at negative. So I'm going to go ahead and just draw like this. And this guy crosses over, so he goes past. At 0, he what? He touches. So we're going to go like this, and it's going to bounce. And then at 1, it's going to cross. So we go from positive to negative, like that. So our graph looks something like this, right? So it has the end behavior of like negative, negative, and then it has the touch, cross, or opposite. This is cross, this is touch, and then now the crosses again to have this. And so yeah, I don't have much time to do anything else, but most of it is pretty recent, like content and material, right? A lot of unicircle stuff, trig stuff, right? All that stuff. So I don't want to cover too much of it because it's still kind of fresh. I wanted to touch more on the earlier stages of things, right? So with that being said, yeah, I hope you guys have a great college career, and yeah, best of luck in the exam. See ya.